Hello, everyone. Hi, everyone. I'm Valentin Schneider. I'm working at ARM, and I'll be talking about Lisa today, and so will Stephen Miao, who's hiding in the back. So we kind of have two different perspectives on Lisa. Mine is more the kernel hacker, and Stephen is more partner enablement. So my side is more, you have some patches that you're looking at that you want to evaluate, and Stephen is more about you have a platform and you want to evaluate how your kernel is running on the platform. So what we'll go through, I think a lot of people in this room know what Lisa is, at least by name, but I'll still go through a brief introduction. And then the two sides of Lisa, one is using it for kernel analysis, and the other is using this analysis to do some automated tests. Also have a bit chat about what's upcoming in Lisa, and I put questions at the end, but actually if you have questions at any time, feel free to interrupt me. Right. So what is Lisa? Lisa is a Python project that we develop at ARM, and it bundles some other Python projects we have at ARM. Namely, we have devlib, which is a device communication abstraction library. So what this means is it's very easy to communicate with your target. So if you have your Android smartphone or your high-key dev board, you have a Python interface to communicate with it, and it makes your life easier. We also have Trappy for trace parsing. So for kernel analysis, we mostly rely on trace parsing. So that can be ftrace or systrace for the Chrome OS guys who usually use that. And yeah, so we also have notebooks. So what are notebooks? They are some sort of IDE that is hosted in your web browser. And they're very convenient because then it's easy to plot some information in them. And every image that you have in a notebook is packaged in the same file, so you can just copy the notebook and send it to someone, and they have all of the information. So for collaboration, it's quite nice. So this is pretty much the same information as I've said, but I didn't want to dump the scary diagram all at once. So this is split in two things. It's not like the shiny future that Joel presented. We are still split where we do some work on our host and then we communicate with our target. So all of the heavy lifting for the communication can be SSH or ADB, and that's handled through devlib. And devlib also gives you some interfaces for simplifying things with the target. So you are entirely free to interact with sysfs or procfs on your target and run some shell commands on it through devlib. But you also have some Python interfaces just because it's more convenient. So for instance, for ftrace, instead of manually fiddling with trace CMD, you have an interface where you just do start and stop, and behind the scenes, it will copy trace CMD to the target, start the collection of the trace with the events you specified, and will copy that back to your host, and you have your trace ready to use. And then, as I said, to actually use this trace, we pass it to Trappy that will turn it into data frames. So data frames are Python structure that's really convenient and really nice to use. So you can do some sorting, some filtering. You can try to look for certain patterns in your data. And that's the reason why you use them, because they're quite powerful. And so yeah, as I've said, in Lisa, once we have these data frames, we can do some analysis, run some tests on these traces, and we have the notebooks. Right, so an example I'm going to use is misfit patch set. So yeah, Vincent has talked about it, so I'll still give a very quick introduction. In Big Little, you have asymmetric CPU performance, and so you need some sort of policy to decide what runs on the bigs. The way we're going was with the misfit patch set, which was authored by Morten, who's working in the same team as I. And the gist of it is, if you have a task that has a utilization greater than 80%, so it's using at least 80% of its CPU if its current CPU's time, we try to move it to a higher capacity CPU. The general idea is, okay, you have a CPU bound task and try to give it some more CPU time by moving it to a bigger CPU. It's been in Android for a few years, but we still had a few issues with migration delays. So this is my test case on the Hikey 960, where you have 4 littles and 4 bigs, and you just have a CPU hug running on a little. and we want that to run on the big instead. And rarely, so it's not all the time, otherwise people would have been complaining way before, it can take a long time. So in this case, it's 350 milliseconds before it moves to a big CPU, which is a lot of time. This is a very simple RTAP 100% task. So whatever CPU it runs on, it will run forever, but we want that to run on big. Just to 350, if you look at over there. The window is 350, but it could go even higher. I've seen 800 milliseconds and things like that. So yeah, that's where I stepped in and tried to look at what was causing those delays and how we could fix them. Mostly involved a lot of trace print case throughout the scheduler. I managed to fix a few things and improve the patch set, but there's one specific issue that I want to show in here, where Lisa was very useful, is that after having all of those improvements, I still, even more rarely, had some long balance intervals, some migration delays, and I found out that this was caused to balance interval. So this is used in periodic load balance. When you are about to do a periodic load balance, you look at when was the last time you did a load balance at the interval, and that's your next time you're supposed to do a load balance. But this balance interval value can be increased when you have some tasks that are pinned to a CPU, and the load balance failed to pull that load. And so it's sort of a heuristic to say, okay, I know that in my current workload, there are some ping tasks that I can't move, so let's just wait it out, increase the balance delay, so that next time I look, I hope that it will be gone. Yeah. So that you don't pull again while it's migrating. Yeah. Yeah. But in that case, that was not the active balance pass that was causing issues. So the thing is, you use this balance interval to compute when's the next time you're supposed to do a load balance. So since this value was very high, we would block any load balancing until we have gone over the delay that was imposed by this value. So it's fluctuating the period at which you do load balances. If it's very high, you're only going to do it seldomly.
I think that you can delay by something like 8 or 16 times. So by default, you have a short interval, but you can increase by more than 16 times. So
by default, it's the size of the span of the get domain.
A log based on the it's a log of the
So the other factor in the load balance taking 300 milliseconds is the pelt signal itself would have taken, I guess if it was starting from 0, it would have taken like 100 and something. So that's also something. That's
also something, but not for those delays there, which is way over the pelt runtime time.
Oh, so it would be
100 milliseconds. Yes, for pelt, it's 100 milliseconds. You starting from 0 to reach 80%, something like that.
Yeah. So that's a part of the 300.
Yeah, maybe.
Yeah, but it's not the biggest part. Right, and so when you have traces like that, Trappy can also parse it and turn it into a data frame, because as long as you have something that looks like a regular trace point, you can parse it and have columns in your data frames. And so what I've done is I plotted it. So I did some filtering to just get the value on the big CPU that I was interested in and at die level. And the interesting thing that I saw is this value gets very high before my test workload is even executed. And that's actually quite nice, because if I didn't have some way of plotting it or having an overview of all of those values, I would have been looking in this area and not understanding what was happening. So I think that's a good example of being able to plot your traces is quite nice. So I had a look in the trace in this area, and devlib was to blame. So it was doing some setup on the target, and it uses BusyBox, but this BusyBox thread is actually pinned to CPU 0, and if the stars align, and at this point you're trying to do a load balance, you will try to pull this task. If it's the busiest group that you're seeing, it will fail, and you'll increase the load balance interval. So yeah, that's it for my first introduction to Lisa and Steven, if you want to talk about the rest.
No, yeah, we can discuss. I send a fix. I have discovered that you have some case where you say we need to do some load balance and the imbalance value is 0. And in this case, you run in the path with the LBF all pin logic, whereas it's not because your pin, it's just because you ask to migrate 0 load. And in the move task, if the imbalance is 0, you just return before cleaning that. So in the load balance path, say, okay, the flag is set, so it's a all pin imbalance. I remove the CPU and redo all the load balance stuff. So there is a fix in mainline now for that.
Good afternoon. I'm Steven from China system support team. I'm an AE and focused on EAS, IPA, and V8 virtualization, and work very closely with the CEO power team. Valentin's Lisa example focus on kernel hack. My Lisa example will be targeted on custom, but it seems customers are more interested in the AI and machine learning topic. So beginning with the first example, it's visualizing kernel function call graph with in a Lisa notebook. This example is show Lisa framework is very flexible and extensible. We can it's very easy to add some external module and import in the Lisa notebook. In this example, we needed to install the Python GraphViz module and import in Lisa notebook. It's a simple Python interface for the GraphViz to join the graph. I think most of you may be familiar with GraphViz tool. Yeah, it's a visualization tools. It's an open source visualization tool, and it defines a simple text-based language, dot language, to describe the layout and structure of the graph, then generate the graph based on the dot file. So we need a Python GraphViz module. Then we get the function trace based on the ftrace function graph tracer. We use a one-line simple trace command to, for example, if we want to get the try to wake up function call graph, we just use this simple command line. Then we can get a C source code like call graph. The first level function is try to wake up, and the callee function is in a pair of brace. Then next level, and so on. So to visualize the call graph.
Sorry to interrupt. It looks like you set the function trace graph nesting level as well, right?
Nesting level.
Because it looks like it's nested only to level 3, I think, or so you don't see a deeper Because that's what I was going to ask you, because if you don't do that, then the overhead is going to be a lot.
Maybe, yeah.
The other problem is if you don't set filters, then you're tracing every kernel function.
Yeah.
All the time.
Yeah, the spin lock, all kind of lock. Yeah. And the next step, we need a Python script to pass the trace log from the root function and pass one line by one line to get the query. And so I found an example on GitHub, which it's a Python module, which name is kernel visualization. Yeah, it's based on the dtrace trace log. So I took this Python script and import in the Lisa notebook to pass the ftrace format. Yeah, it basically creates a function call tree from the root node and the callee function node. So after build the trace tree, we just travel the tree to dump all the callee to the dot file to describe the call graph. Then the last step, we use the GraphVRZ Python module, just import it to visualize the function call. Yeah, the whole call graph is very big, so it's just part of the call graph. Yeah. It is very useful to do some code deep dive to custom. Next example is KVM performance analysis on Hikey 916 board.
Sorry, before we move on to the next topic,
okay.
I was wondering this script should, like trace command can call Python directly.
Trace command?
Yeah, so you can probably submit this to the trace command project, and then it'll be useful for everyone.
You mean this?
Yeah.
This notebook?
Yeah. The whole graph is. So you need Lisa for this stuff, do you?
Not necessarily.
Okay, so if it's just Python and Python libraries and other C libraries, then you can just write a plugin for trace command.
Yeah.
And that'll be super useful, I think.
I can reformat the notebook, then upstream send a pull request.
Yeah, to trace command project.
Trace command?
Yeah, so
it's just
so I'm saying like you you generated the function graph data, right? So when you generate it, you can write a Python script. This is not Lisa or Trappy or any of that. This is just you can ask trace command to call Python functions every time a function is hit, and then you can probably generate your dot file in that, and then send that to GraphViz to get this.
Okay. I don't know if the Android static build
so you can just use
trace command can support a Python script.
You can use the last talk that the topic of the last talk, right? You can run trace command using ADEP. Were you there in the last talk? Or you were not there in the last talk? Okay. Yeah, you can use AndroDep to.
Oh, AndroDep.
Yeah.
Okay.
To run Python trace command, and that's one of the reasons to use it. Because you have to disable that.
Mode.
Yeah.
chroot to run the full functional trace command. Yeah. And next is the KVM performance on Hikey 916. I did this performance analysis because more partners ask for the ARMv8 virtualization about the performance and the implementation. on the ARM platform. So I did a KVM test on the Hacking 960 board. So this is the architecture of KVM on Hacking board. So to bring up KVM, we need to load the kernel from UEFI. So you can boot at ER2 to initialize the hypervisor, the low visor on at ER2. Then we start a kernel, host kernel and a KVM module at ER1. Yeah, it will create a CPU thread to run guest OS and enable stage 2 translation. And then jump into the guest OS. The right side is the guest OS. And the parallel virtualization driver in guest OS will co-work with the backend driver in the host OS to do the device I/O emulation. Yeah. I did some roughly test based on Sysbench, like a RAM bandwidth test, a CPU test, and a file I/O test. And we can visualize the test result in the Lisa notebook. We can see the result. Maybe the font is too small. The right is Sysbench RAM test. We can find the blue bar is in guest OS, and the orange is host OS. We can see that the RAM bandwidth is almost the same. Even guest OS enable the stage 2 translation. It can be up to 24 translation table work if TRV missing. But the RAM bandwidth is almost the same. Yeah, and the CPU performance in guest OS and in host OS is very closely. For the file I/O test, we can find that the I/O bandwidth in guest OS is significantly lower than in host OS. Yeah, this is a bottleneck on ARM v8 virtualization, I think. Back to the architecture. Yeah, because each time the front end virtual driver request I/O, it will trap to ER2, then trap to host OS ER1. Then host OS will do the real hardware I/O, and after finish the I/O request, it will trap to ER2, then switch to ER1 in guest OS. So maybe it leads to the latency, the I/O latency. Yeah. This is a system call function profiling based on the Lisa function profiling function. We can easily virtualize the system call in guest OS and in host OS. You can find the average system call, like system call, like sys read write, sys open 8 and 6 clock get time, the average execution time is long in guest OS than in the host OS. It brings too much latency in the guest OS.
Was the cache hot or was it cold cache?
I think the cache is hot for the sysbench test. Yeah, the latency come from the too much trap. This is because High-Kinetic board is ARM v8. If we have ARM v8.1 VHE extension CPU, the host OS will run at ER2. It can reduce half of the trap between host OS and guest OS. Yeah, because currently we have high visor in at ER1 and low visor at ER2. Yeah, too much context switch for the ER2 will save ER1 context and switch guest OS to host OS.
So basically every syscall would have the same switch.
Every IO bounded syscall.
Every syscall also switches you switch from EL0 to.
Yeah, syscall from ER0 to ER1 in guest OS. Then guest OS, for example, if it is IO virtual disk IO request, then it will request here the front end driver in guest OS at ER1 will through the virtual IO interface to communicate to the back end driver in the host OS at ER1. Yeah, but it happened in one CPU because ER switch just can trap to current CPU. You know?
Yeah.
It can switch trap to another CPU's ER2. So it must save the ER1 context, all the context, and then switch back.
Mm-hmm.
This example is from a customer issue. They reported on their too big, too little platform. Their boosted task will always peg to the last big CPU. Yeah, so I create a Lisa notebook to analyze this behavior. Yeah, it's based on the 4.9 kernel. Yeah. Because for no latency sensitive task path, even it is a boosted task, find best FBT will select the max spare capacity CPU. Yeah, so the max spare capacity means capacity original minus new util. For a boosted task, new util equals new util will select the max value of boosted task utilization or the current CPU utilization plus task utilization. So this is our case assumption. So for a small boosted task. Say the utilization for the task is 100, so the boosted task utilization is 562. So it will, in FBT, it will pass all the small CPU. Then the target max spare capacity for the big CPU is 462. So it will select the last big CPU almost every time. So it tends to be a fixed order to select the max spare capacity. So after the first task placed on the last CPU, CPU 3, if a new task wake up with if its utilization is 10 and it is also a boosted 5%, 15% task. So the new utilization is 517. So it will select the max spare capacity CPU. It will select CPU 3 again. Yeah, this is our assumption. Because for the no sensitive task path, it tends to be packed. The EAS have a packing task strategy, while it try to spread the task. If the CPU can running on a lower OPP. So we create a Lisa notebook to reproduce this case assumption and analysis. Add some customized trace sprint K, like Valentin did, and the Trappy in Lisa. Trappy model in Lisa can catch this custom signal and plot the CPU residency. Yeah. We also can create a filter to, for example, we just want to check task 6. So we can use a filter to check the task 6, the new utilization and the max spare capacity. So the last is the CPU residency plot. We can find our task 5, 6, 7. We'll select the last big CPU at first. Yeah. The CPU 7. Yeah. After a while, it may be pulled to other big CPU. Yeah. Next is automate test.
Right, so we've seen that with Lisa we have a few tools to do some analysis on the traces, and the next logical thing to do was turn that into tests that then we can automate on our boards and try to see if things break or if patches do what we expect them to do. So for the tests that we have in Lisa, most of them use RTApp, so I think we've already talked about RTApp, but it's just an easy way to create tasks with a given utilization that we want. So in terms of tests that we have, the main test suite we have is about EAS. So I'll go into details on this one on the next slide, but it's really just making sure that EAS is doing what we expect, which is reducing energy consumption. We have a sanity test for CPU Freak, which has shown that it's quite useful. So even if you have CPU freak and say you use the user space governor and you try different frequencies, and then the CCFS does say, yes, you have this frequency, sometimes you actually need to check that in the hardware you have the frequency that you've requested, because for instance on the Heikin N60 we had a broken CPU freak and realized that if you run sysbench at every single OPP, you always get the same score because the frequency is actually not changing. So this is a sort of test. It's quite useful to make sure you have something that's reasonably sane. Hot plug is kind of the same kind of test where you hot plug in and out a lot of CPUs and then you try to see if your target survived the torture. And again, that is useful when you have some like hot plug lock problems and things like that. It's a nice test. And then we have some few others. So load tracking signals. Since with RTApp we can create a workload where we sort of know what utilization it should have. We can try to then compare with the actual signals that we have and sort of get an idea if it's broken or not. And since I had some workloads to make sure that misfit was working, I turned that into tests. Right, so for the EES tests, one that is actually very interesting is the task placement. So with EES, we want to minimize the amount of energy we spend. And so what we can do is, since we know what kind of task composition we're creating, we can compute an expected, an optimal task placement. So here, for instance, our workload is, we have as many tasks as big CPUs. So this is Heikin N60, so we have 4 tasks. And then we just have 2 phases, one phase where it's low utilization, and the other phase where it's high utilization. So in the first phase, we expect it to run on the littles, and in the second phase, we expect it to run on the bigs. And then we just repeat that one more time. So since we have the energy model, we can compute what the expected utilization landscape look like, and then compute an estimated energy consumption. So this is just using the energy model that we have for the target. And then when we run this, we can do exactly the same thing. We can see, okay, this is where the tasks were placed. We have the energy model, and we can compute how much energy that would have costed. So there's no actual energy measurement, but this is just estimated energy. And then the test makes sure that, okay, what energy we think we have spent here and what energy we should have optimally used, the difference must not be greater than 5%. And when we run our tests, this is working pretty well. It's just a good example that EES is doing what we want. And then as an example of how the APR looks, half of it is actually just figuring out how many tasks you want and how much utilization you want. But then the API is fairly simple with that. You just say which utilization percentage you want and how many times you want to loop. And I think that's a good example that you can create different workloads with different task compositions fairly simply. Another thing, so every 2 weeks we assemble all of the patch sets we have for mainline, and we rebase that on tipshed core. So this is Ingo Molnar's work in progress 3 in a way. And we run all of our tests for 2 days. And then we do a bit of statistical analysis, and it tells us if we have some significant changes or not. So this one was at the beginning of August this year, and we can see, for instance, that we had one of them where we had significant regression, and the p-value was really low. So we are really sure that this is not just testing noise. In that case, actually, if I remember correctly, it was system D that had created a lot of tasks, and that was just corrupting the tests and influencing what we were doing. Okay, so this is for the Linux testing side of things. Steven can take it over for Android and wltest.
Okay, me again. wltest is a new automated test framework for benchmark Linux scheduler and EAS improvement. It's based on Lisa and workload automation version 3. To run, it's pretty good to run a batch of tests, then use a Lisa notebook to analyze the result. Yeah. It's intended to do the full scheduler evaluation for the EAS. For example, for the parrot vs word comparison. Yes, the wltest workflow is we run the wltest command in the Lisa console, then it will auto build, then auto test, and output to the result directory, then run several rounds, and at last, the post-processing Lisa notebook to do some data visualization. Yeah, it's very cool, but some partners have their own auto test and auto build system. They don't need our wltest auto build and auto flash. They just want auto test and do the full scheduler evaluation. So yeah, I did some trick for the partner to integrate the wltest to their auto build, auto test system. Yeah, by default, wltest will compare the different test results based on the kernel version. But some partners think they just want to do different tests, use different config with a same kernel. Yeah, so besides the kernel version, the SHA-1 ID compare, we can classify the test with test tag, like test 1 and test 2. Then in the scheduler evaluation notebook, it can compare different test tag. Yeah, this is an example for parrot vs word. Also use the base tag is word and parrot tag against the word tag to compare. This is a box plot for the comparison. Yeah, it is just a trivial trick for the wltest. Next is the future of the Lisa.
Right, so for the future of Lisa, there's a few things that we're working on. Most importantly, maybe Python 3. So a lot of things for Python 2, the support is getting near 2020. So things like data frames and all of the scientific packages, they're going to end their support. So now is a good time to switch over to Python 3. You've seen the integration report with all of the statistics. We're planning to make that public as well. And we are going to switch the API for the kernel test. So the example I've given that was nice and short, that's the new API, because the old one was actually quite convoluted. And if you wanted to go out of the beaten path, it was a bit more complex. So the reason for that is also that we've been using Lisa for a few years, and now we have a better idea of what we actually want to do. So it's a good time for a redesign, and at the same time, we can try to make it a bit more CI-friendly. One thing I'm also insisting on is documentation and ease of use, because Lisa is not really great on that front. And so we're making the documentation as good as it can be in the hopes that eventually some other people can also contribute the test cases. So in terms of roadmap, this mostly started in August, where we have the test execution API rework, and also what we use to actually run the test. So how we collect all of our results and build the statistics. September is still mostly about porting the tests we have in new API. That's almost done. And Python 3 migration, since Friday of last week, we're actually running Python 3 now on our internal branch. Next month, that's where we're gonna use that more internally so that both developers and also CI use that so that we can try to iron out the remaining bugs we would have. And in November, our hopes would be to do an external release, so have a new branch on the official repository, and after some period of time, we are aiming for 6 months, we would switch the main Lisa branch to that new version. And yeah, of course, one thing we want is more tests that either we come up with or that some other people can contribute. A small preview for people who want to relook at that through the slides, and yeah, that's it. So if you have questions or otherwise, I'm done.
So, yeah, one of the things I've been thinking about is, you know, Trappy is kind of slow, right? Even with like decent sized traces. So I was thinking, where is the bottleneck? So it seems like you know, I don't know about Panda's internals, but you know, so even if Trappy was, say, written in C++ or something, and it was multi-threaded and doing parallel trace parsing and building data frames in parallel, but I'm not too sure whether Pandas is still the bottleneck.
No, so Pandas is actually very nicely optimized for large data sets. I think the bottleneck in Trappy is actually parsing the trace, because we're only doing that at once. I think we have a work in progress patch set to try and divide the file in multiple chunks and then do the processing on those, and then you fit that in the same data frame. But I don't think it's been touched in a while, so we should revive that maybe if there is the need. It's just that for now, with the cache that you have, usually you run your tests on the CI, and then you clone that, and you already have the cache that's been created, and usually it's fast to load it again. But if you actually have use cases where your trace is really huge, that could be an incentive to do that.
Yeah, and the other idea we discussed before was to parse the binary directly from trace.dat from trace command, instead of, right now it's all text-based, right? So, you know, there is a libtrace command in trace command, which you can use to write native code to get access to the trace records directly instead of the text.
Yeah,
so
yeah, that would be another optimization, yeah.
That should speed it up too quite a bit.
Right. Thank you, everyone.